tell you about, first one, I'm going to introduce ASCAP and the EMU survey. So ASCAP is this big new radio telescope. It's an SK Pathfinder, but it's actually a fantastic telescope in its own right. So like Meerkat in South Africa, what's happened with SKA is that it spawned off these fantastic telescopes, which are already doing great science, and eventually SK will do even greater science. But in the meantime, there's an awful lot we can do with these Pathfinders. And so the Continuum survey on ASCAP is called EMU, which stands for Evolutionary Map of the Universe. And sorry, that second line, that mission is, that's for a PR thing. I apologize for that. Now, the great thing about ASCAP, it's got this enormous survey speed, which I'll show you in a second, but the minus is that this produces enormous volumes of data. So the data rate, you can see, oh, can you see my mouse? Right, okay. So that checkerboard thing up there, that's the phased array feed, and basically like a radio CCD array. But the minus is it produces this enormous data rate, 100 terabits a second. And even after we've processed all the data and produced images and so on, our processed data volume is 70 petabytes a year. And we can't actually afford to store all of that. So we only store 4 petabytes a year, and we have to make a decision about what data we're going to throw away, which is quite painful. Okay, so that's our challenge. So the EMU survey, our plan is to survey the whole sky up to declination plus 30 for radio continuum. So some of you will be familiar with the NVSS, for example, which did all this a decade or so, a couple of decades ago. But obviously 2 decades further on, it becomes much bigger. So the total number of radio sources known in the sky at the moment is about 2.5 million, and EMU will discover about 70 million. So just this one survey significantly increases our knowledge of the radio sky. And obviously our plan is to make lots of discoveries and answer questions and so on. But probably the interesting thing for this audience, this conference, is the way we do with astronomy, which is large N astronomy, which, I mean, there's obviously a few telescopes around the world which are entering this era. Now, to give you a feeling for what this means for radio surveys, this is a plot of all the radio surveys over time since way down there on the bottom left corner, Grote Rebus discovered radio astronomy and did a survey of one source, and then it goes up through Hay and Bolton and Mills, and then the Cambridge surveys, and it gradually increases with the time, so you get this enormous spike in the 1990s with NVSS from the VLA, and first from the VLA, and events and sums from the Netherlands and Australia below them. And after that, after NVSS had done those surveys, there isn't much more you can do until the technology improves. And so 20 years later, here we have another great big spike, and you see up there EMU and LOFAR, Aptiv and VLAS. Meerkat ought to be there in a sense. Meerkat's also a very fine telescope, but it's optimized for a different part of the parameter space, so it doesn't show up in this diagram. So radio astronomy is about to change significantly with these. Within EMU, these are the sort of projects, science drivers we have. So EMU is very much an international project, although it's led from Australia. About 300 people in 21 countries, part of the EMU team. And as you can see there, most of the science projects are actually driven by non-Australians. So it's very, very international. And our overall goal is how do galaxies form and evolve? Okay, now let's get on to the, I'm not going to talk about the science, by the way. My apologies if you want to hear about the science. I'm going to talk about data. But to give you a taste of the sorts of things we'll do, we have a significant cosmology project within EMU, and we have a number of different observational tests. But this is an example of one. If you take a nice big foreground galaxy, you can see on the right there, it bends the space around it and so affects the background grid of distant galaxies. So I've shown them as though just a rectangular grid there. And the lensing of that foreground galaxy does two things. Firstly, it moves the galaxies apart, the background galaxies apart, so that in a flux limited sample, the numbers of sources per square degree decreases, but it also makes them brighter. And so the number of sources per square degree increases. And so what you actually observe is a difference between two effects. And so this is very sensitive to how gravity works over large distances. And so this we can test where the general relativity still holds over very large distances. Now people have detected this effect in the optical, and they do it by finding a nice big foreground galaxy or cluster and looking for the effect on the galaxies behind. But because we've got millions of galaxies, we don't have to go through that painstaking process. All we have to do is do a cross correlation between our foreground galaxies and our background galaxies. But to do that, of course, we need redshifts. And that's where this segues into the talk. But you see, all we need to do, we don't need to know the redshift of all those individual galaxies. What we want to do is to take all our galaxies and put them into two bins for this particular experiment. We want, let's say, galaxies with redshift less than 1/2 and galaxies with redshift greater than 1, with a sort of guard band in between them, so that you don't get the same source appearing in the two bins. And simulations show that we should actually be able to do this really well with EMU, provided we can get the redshifts. So that's the critical thing. We need to be able to measure redshifts for 70 million galaxies. So in this plot on the right, you can see we have a problem, because on the left, that's the distribution of redshifts in Sloan, and they're nearly all less than 1. And you can see those other plots like radio IRFOS, those are high redshift radio sources, and radio sources tend to be high redshift. We need 70 million redshifts. All of spectroscopy can only give us a few million, and most of those are low redshift things, which are probably not radio sources. So we have a problem. Another illustration of that, if I show you the redshift distribution of radio sources in EMU, of the overall redshift distribution of all sources will have a median redshift of about 1.4, whereas I've just shown you that the spectroscopy tends to give you redshifts less than 1. So that's the problem that we're trying to tackle. Now, the good news is that for most of our science, we don't actually need them to be accurate. So here's another experiment we plan to do using our cosmological parameters, looking at the clustering of galaxies and so on, and effects like the one I've just shown you. We can measure the non-Gaussianity of the distribution of galaxies. And what that is actually, you're actually looking at the noise in the Big Bang, or technically in inflation, and you ask the question, is that noise just stochastic, or is there physics driving it, like cosmic strings or something, or some sort of discontinuity or singularity? And so the critical thing here is the FNL, which measures the non-Gaussianity. Apologies. And what this plot shows you is the standard error that you measure on FNL, sigma of FNL. And so here's how different instruments perform. And you see the horizontal black line, that's what Planck is measuring at the moment. And just below there is the dotted line that Euclid will measure in a few years. Now, up there on the top left is the black square, and that's, if you took EMU and just measure things like the autocorrelation function of the EMU catalogue with no knowledge of redshifts, that's where it puts you, which is not a terribly interesting measurement. But if we manage to sort all our sources into two redshift bins, you're now in the second column, see just there, and then you can see we actually do better than Planck, not as well as Euclid. It's actually still a useful thing to do, because this is a completely independent measurement from the way that Planck is measuring it. If we can put all our sources into 3 redshift bins, then we get down here and we actually beat Euclid at this measurement. So you can see that even if we can take our galaxies and just put them into 3 redshift bins, we can start to do really exciting science. So when I talk about measuring redshifts for EMU, I'm really, pardon me, I'm talking about a relatively small number of bins. By the way, SKA, this is SK2 in maybe a decade or two, then goes a factor a few deeper. But you can see that EMU is already doing pretty well. Okay, so obviously we're not going to use spectroscopy. So what about photometric redshifts? And there we have the problem that you look at all the work that lots of very capable people do on generating algorithms for photometric redshifts. And the trouble is that what most optical people are interested in is getting really accurate redshifts from photometry. They're not interested in putting things into low quality bins. The other thing is that most of the existing work, you look at the fantastic work done by, let's say, Mara Salvato on the Cosmos field, and she's got incredibly good photometric data, 31 bands in the Cosmos field, most of them measured pretty well simultaneously. Whereas we, in EMU, we're reduced to using data from the various all-sky surveys. So we don't have that fantastic quality of photometric data, but we're not after really accurate redshifts either. The other problem is that you look at the work that people are doing in photometric redshifts, and they tend to use either templates or training sets that really don't correspond to the sorts of objects we're looking at in big radio surveys, high redshift, radio loud, AGN. Most of those templates are derived from low redshift SEDs. In radio, we have there's very strong evolution of radio sources over redshift, far more so than with optical sources. And the other thing is that we do have very good radio data, which at the moment is not used in photometric redshifts. There's another thing, there's a good reason why existing codes don't use radio data. Firstly, the existing radio surveys don't give you very good fluxes. They're, up to now, the big radio surveys have been relatively insensitive and don't really see the same objects that most optical astronomers are interested in. That will change with EMU. We will see a large fraction of the ordinary bog standard star-forming galaxies that are of interest to people. The other thing is that you look at this spectrum here, and the quote from Jim Condon, he said, "There's nothing as useless as a radio source." What I meant by that is that you look at the SED for this radio source, and it's a power law. And the wonderful feature of power laws is that you can redshift them to anything you like. They're still power laws. They give you no useful information. But that's 20 years ago, and modern radio data is significantly better, and we have these feature-rich SEDs. And so here you can see a turnover at the low end due to the energizing mechanisms, a bend at the top end due to inductance running out of energy. And so given something like this, you can actually measure a redshift, provided you understand the physics, or if you have a good training set. So we can use radio data now. Okay, so all that was just setting the problem. So what are we doing about it? So one thing we have done is we formed a thing we call SPARCS, is the SK Pathfinders Radio Continuum Survey Working Group. And we formed a group, a discussion group, to compare techniques on redshift measurement. So that includes groups obviously from us in Australia and South Africans, people working on LOFAR and VLA and so on. And we're comparing notes on our redshift algorithms. And what we're really doing is exploring what algorithms can you develop specifically for radio surveys. And because the reasons I've already said, they might be a bit different from what people have been developing for optical surveys. So we want to use the relatively low quality photometry that's available for all-sky surveys. Our goal is not to get high precision, but to get reliability, to get a low outlier rate. And we've got very large sample sizes of millions. If anybody wants to join this, just email me, and we're organising teleconf next week at the moment. Okay, so we started this process a long time ago. Actually, this effort was initially led by Mara Salvato, and recently I took it over and we submitted a paper on it. And we were asking the question, what techniques work best with the sort of data you get from radio surveys? And you're not supposed to see the details here. This just gives you an idea of the sort of thing we did. We compared standard conventional photometric template fitting with different algorithms, neural net, random forest, and the k-nearest neighbours. And so just to show you we did the comparisons. The result of that was that all of these techniques work quite well below z equals 1. And as soon as you get above z equals 1, few of them work well. And that's basically because the training sets we have, or the templates we have, are really based on low redshift surveys. But what was also interesting is that you take a really simple algorithm, the k-nearest neighbours, what it does, you set up a parameter space with all your measurements, your features, and for any unknown galaxy, you just look at the nearest neighbours and you measure their redshifts, and you take some sort of mean of those. And you think that is so dumb, that cannot possibly work. But actually, it works almost as well as more sophisticated algorithms like random forest. So if you take a field like Cosmos, we found the template fitting does work really well. But once you get down to lower quality data, the machine learning actually outperforms template fitting and does surprisingly well. So in this test, it is generating something like 80% of the sources were getting a good redshift. And by the way, so on the right here, this was one of our best results with fairly poor data. This is random forest run by people at Johns Hopkins. And the interesting thing here is, if you look at the residuals down in the bottom plot, you see there's a systematic trend. That's only that this algorithm really hasn't done its job, because looking at that, I can fit a straight line to that data, and I can go back to the algorithm and say, hey, if you do this correction to your data, you'll get a better value of the redshift. Well, of course, I shouldn't have to be doing that. The algorithm should be seeing that itself. And so that's telling us, yeah, we can do a bit more work and get it to work a bit better. Sorry, my voice is going. Recent work, we've continued working on the same direction. My student, Kieran Lucan at Sydney Uni, has been exploring this, working with random forest and k-nearest neighbours, and finds that under a number of conditions, you actually get comparable results from k-nearest neighbours and random forest. So this is an example on the right where this is using KNN regression, and he's done things like a lot of data preparation, seeing what the important features are, looking at the data, using the data to tell you which are the important features, and rather than using simple Euclidean metric, using this unpronounceable Mahalanobis metric or something, which takes account of the data. And as you can see that on the right, you've really got a really good fit of the photometric redshifts to the spectroscopic redshifts with only 5% outliers, and the residuals at the bottom don't have one of those annoying trends. So it's actually working really well. The other thing that occurred to us when we were doing this is that, given that we want to, for most of our science, we actually want to bin the redshifts, isn't this a classification problem rather than a regression problem? Can we actually do better by putting the redshifts into bins before we run the algorithms, and seeing if we run it as a classification problem? And that shows the result of doing this. This is KNN, but doing a KNN classification, trying to bin the redshifts, asking them which box does this redshift fall into. And at the moment, that's actually given fairly similar results to run it as a regression. But in principle, we might do better. So we're continuing both of these strands. It would be interesting to see whether, because in principle, you need less information for a classification problem. So in principle, it could outperform the regression, but we'll see. I think the great thing in all this machine learning stuff is to suck and see and try things out. So far we've tried, so I should say those results were fairly deep data. We also tried EMU-like photometry by just throwing away the faint photometry. One thing we want to try is we're now starting to get data with ASCAP, and we should be using real photometry data from ASCAP, plus things like SkyMapper, which Chris Wolf is about to tell you about, and VHS wise and so on. We also want to use the radio data and use all the richness we have in the radio SCD. At the moment, we're also throwing away missing data, but missing data tells us a lot. So I'm showing you this plot again. Those things called IFRS, infrared faint radio sources. Those are sources where we've just used the selection criterion, that it's a strong radio source and it's got no WISE detection. And as you can see from the plots there, that basically guarantees you that it will be at Z greater than 2. So just a non-detection of WISE is giving you a lot of information about the redshift. So we really need to use those non-detections. Another thing we can do with these redshifts is the idea of statistical redshifts. Maybe we're not really interested in the redshifts of the individual galaxies. Maybe we're interested in the redshift of a population. So going back to this problem here, I said what I want are 2 samples of galaxies. I want you to take all the EMU sources and give me 2 bins, one at a redshift below 0.5 and the others with redshifts above 1. And then show me the redshift PDF for those, the probability distribution function. How would you actually go about that? It's actually very simple. So if you want a low redshift galaxy sample, I haven't actually tried this is just a thought experiment. If I select all the galaxies that are faint in radio, resolved in Sloan, and fairly bright in the optical, that will give you a low redshift galaxy sample. Finding galaxies which are strong in the radio and weak in the infrared, as I showed you earlier, will give you high redshift galaxies. So with very simple rules, you can select out populations. Then when you do the SCDs of the individual galaxies, they might be a bit rough, but of course you've got lots of them. So you can measure the redshift PDF of the sample by summing the individual PDFs. So this is an important point. When we do these photometric redshifts, it's important we don't just get a single number out at the end, but we actually store the probability distribution function. And that means we have to use an algorithm where we can measure that. So there's a bit more work to do on machine learning to be able to do this. But clearly this is all possible stuff. Okay, so my time is running out. I'll come to a conclusion. I should say that what I've described is probably obvious. It's a progress report rather than a finished product. This is avenues we're exploring at the moment. But what we are seeing is that the challenges we're facing in measuring these photometric redshifts is quite different from what people have been doing traditionally for photometric redshifts, both in our aims and data availability. We're exploring classification, which we hope may turn out to be better. But when we take these numbers together, our best estimates at the moment is that about 70% of EMU sources are going to have reasonable photometric data from things like WISE and VHS and SkyMapper. And what these experiments are showing us that about 95% of these are going to give us usable redshifts. So more than half of our EMU sources are going to have usable redshifts, which is about twice what I originally estimated when we started the EMU project. So I'm really pleased about that. Important things, even non-detections give you useful redshift estimates. I meant to put here the other things we do need to figure out ways of measuring probability, density function, and we haven't yet figured out how to use the radio data effectively. I'll stop there. Thank you.